So this is going to be a video showing how to use MNOVA to do the two-dimensional NMR analysis and assignment of all of the proton and carbon peaks in gemcitabine right here, which here's the structure. It's a prominent chemotherapy drug, but it's also a really good introductory molecule for showing how 2D NMR works and how it can be used to definitively assign all the protons and carbons in this structure. You'd be pretty lost trying to do this without two-dimensional NMR, but 2D NMR will do a lot for you and remove all of the ambiguity in which signals are which. I have a multitude of spectra here to work with. I have a typical proton, I have a typical carbon NMR. We can see there's some bad phasing with some peaks dipping below the baseline here, but we can correct that in a little bit. I have a cozy 2D spectrum, which shows proton-to-proton coupling. I have an HSQC, which shows single-bond proton-to-carbon coupling, so essentially it tells you which protons are on which carbons. And then I have an HMBC spectrum, which is showing two or more bond proton-to-carbon couplings, so which hydrogens are near which carbons, but not actually bonded to those carbons. But before I get into actually assigning all of these peaks and going through the characterization of this molecule, I want to first make sure my spectra are fully set up and ready to be analyzed and characterized. And there's a few things I need to do first. The first thing I'm going to do is I'm going to correct the phasing and the baseline on both my proton and carbon spectra. They look pretty good here, but the proton at least looks pretty good, but this carbon definitely has some bad phasing here. So what I'm going to do is I'm going to hit Control and click on both the proton and the carbon to select both of those together. And then in the Processing tab here in MNOVA, I'm going to hit Auto Phase Correction and Auto Baseline Correction. And we didn't really see anything change here in the proton, but over now here in the carbon, we can see that those badly phased signals have been corrected. MNOVA usually does a pretty good job of doing this automatically. You can just hit the auto phase correction and auto baseline correction, and it usually works pretty well. You usually don't need to go back over and redo it yourself. So with the phasing and baseline correction done, now I want to go to my proton spectrum, and I want to go over to the Analysis tab, and I'm going to hit Auto Integration to get the area of all these peaks, and I'm going to hit Auto Multiplet Analysis so that MNOVA can tell me what the multiplicity of these various peaks are. You can see that it's ignored the water signal and the DMSO signal here, which is handy, so I know I don't need to worry about those, and it's done a pretty good job of identifying what each multiplet is, doublets and triplets and multiplets, so on. MNOVA, again, it usually does a pretty good job of this. If we spot any inconsistencies later while we're doing the 2D analysis, we can correct those. The other thing I want to do here is I want to reference my spectra. So I'm going to zoom in on my DMSO peak here because I want to make sure that the x-axis on my spectrum is correct. So I'm going to go to the reference tool here in the Analysis tab, and I'm going to click on the center peak of my DMSO peak. That brings up this window. I'm going to hit Solvents, and I'm going to scroll down to dimethyl sulfoxide D6, which has a shift of 2.5, and I'm going to hit OK, and you'll see it'll nudge that peak over to where it should be. I want to do the same thing in the carbon NMR, so again I'm going to zoom in on my carbon signal here, click on that, go to Solvents, and select DMSO, and we'll see that that's going to shift over and correct a little bit. One other thing I want to do in my carbon spectrum is I want to do peak picking. We can't integrate carbon spectra, but we can have MNOVA identify the various peaks for me. So I'm going to be in the same analysis tool, and I'm going to hit Auto Peak Pick, and we can see now it's snagged all of these various peaks. So that's usually, again, MNOVA does a pretty good job of this. You don't often need to babysit it, but if we need to do anything later, we can. I also want to reference my 2D spectra. It's a little bit different referencing 2D because you have to make sure that you're referencing along both the X and Y axis. So I'm again going to go to that DMSO peak, hit reference, and I'm going to click in the center of it. And you see the reference window here looks a little bit different because it's asking for F2 and F1, so both the X and Y axis. I'm going to hit solvents, and I'm going to again select DMSO, and then I need to hit the reference tool again, click on the center of this peak, and then I need to go to F1 and select DMSO, and that will correct both the X and Y positioning of that peak. I just did that in the cozy. Now I'm going to do that in the HSQC as well. Pretty much the exact same process. The only difference is that now you're dealing with F2 being a proton spectrum and F1 being a carbon spectrum. So I'm just going to do the exact same thing here, where I click in the center of this peak, go to the reference tool, go to solvents, select DMSO, and I'm going to do the exact same thing here in the HMBC. It turns, I mean, looking at these shifts, they're actually very close to what they should be anyway, so we probably could have gotten away without doing this for this particular set of spectra, but it's just good practice to do anyway. Sometimes you'll see two-dimensional crosspeaks having really strange shifts in positioning. It can be hard to tell which peaks are which. So just like I integrated and did peak picking on the one-dimensional spectra, I want to actually do peak picking on my 2D spectra as well. So MNOVA will grab all of these for me, and it should ignore all of these diagonal peaks that are just things coupling to themselves. So if I hit auto peak pick, we can see, yes, it's ignored everything on the diagonal, but it's grabbed all the actual interesting cross peaks here for me. And I can do the exact same thing where I just hit auto peak pick. It snags all those things. It even tells me, hey, this is DMSO, don't pay any attention to it. And then I can do the same thing here in the HMBC. And the absolute last thing I need to do here is I want to drag my referenced spectra, so my corrected one-dimensional proton and carbon spectra, I want to drag it onto my 2D spectra. So what I'm going to do is I'm going to go down to my cozy, and I'm going to then drag my proton over to both the top and side of my 2D spectra, just to make sure that these spectra have been referenced, so their shifts are correct, but the 2D has also been referenced and corrected, so now they should match up. I'm going to go to the HSQC and do the same thing, dragging the proton to the top axis, the carbon to the side, and do the exact same thing down here with the HMBC, dragging proton there and carbon there. And with all of that done, we are now fully prepared and set up to actually go through and process this molecule. We've got all of our spectra peak picked, integrated, referenced, and phase corrected. Everything is good to go, and in the next video we'll get into how to actually start assigning and characterizing gemcitabine.